Hello, good Monday. Um, Today, we're going to finish off the traps and we're going to finish off insulation. We'll take a little look at thermal conductivity, which is something that we cover under the insulation bit. So basically, once we finish all that, we'll be finished A2 Chapter 5. And then when next we meet, we'll be on A2 Chapter 6. And A2 Chapter 6 is about valves and actuators. There's really not a lot of stuff in there. We'll probably finish that off on Tuesday, tomorrow. Maybe going to Thursday, but I don't think so, which really puts us a little bit ahead of schedule, which is really, really good. And then, as for this weekend, a little bit of a reminder that we got a quiz. And maybe what we'll do is if we bang off valves and actuators, what we'll do on Thursday will just be a Kahoot day. And so Thursday, what we'll do is just a bunch of review Kahoots to put you in a good position for that quiz that's upcoming this weekend, which covers chapters 4, 5, and 6 of A2. Really, it's all the piping related stuff. Okie dokie. That's our plan. So let's do this. And I thought I'd share with you some good news. By the way, in general, the midterm was done pretty well. And but this 9 degrees tomorrow, 4 on Wednesday, 9, 12, 7, 8. I mean, I know it's Calgary, and on any given day you could put a negative in front of those, but still, it's really nice to see all of these positive temperatures coming up. I'm pretty excited about that. So here is where we left off. We went through the thermodynamic and thermostatic and the mechanical trap, how those things, the principles of operation. For some reason, just kicked me out again. That's okay. So we know the principles of operation. We took a look at it. We looked at it a little bit differently than the text looks at it. The text is kind of just a rehash of fourth class, which I hate. So let's talk a little bit about subcooling and saturation curves and how a trap may track that saturation curve, or it may have a fixed temperature discharge, and then what are the consequences of each types of trap in terms of how they respond to that saturation curve. And whenever we're talking about that saturation curve and having a trap that tracks it, really what we're talking about is a trap that relies upon subcooling to discharge. So in other words, the thermostatic traps all require subcooling to discharge, whether it's pressure balance trap, whether it is a liquid expansion trap, a radiator trap, bimetal trap. They all rely on that. Now, once we get into the mechanical traps, the floating thermostatic doesn't care whether it's subcooled. It'll discharge the condensate because it is responsive to the density difference between condensate and steam, right? So anyway, I digress. So in terms of trap sizing, I think we went over this already. And so when we select a trap, which is something that we're going to have to do when the trap is broken and needs replacement, or the poor old thing is worn out and we just can't get parts for it anymore. You got a trap that was installed in 1955, and nobody makes that trap anymore, that type of thing. So that forces our hand that we're going to have to purchase a replacement trap. So we have to decide, do we want to use this for a warm-up condensate load, or do we want to use it for a normal operational load? And there's going to be a difference. So here's my steam pipe, and we know that some traps are pretty big and some are small, and really this is a good indication of its ability to discharge condensate. So if I have got a trap that is designed to do an automatic warm-up, that means that the trap is going to have to handle all of the condensate that forms during that warm-up period. So in other words, we need a big trap that costs, a lot of money. Or alternatively, we can have a trap that is designed to handle the small amount of normal condensate that occurs during radiation, radiant heat loss through the pipe insulation. So we always get a little bit of condensate forming, and if we only got a little bit of condensate forming during normal operation, why do I want a big expensive trap? Well, let's save money on the trap, and we'll put a small trap in there that costs much less money. But now we still have to deal with a warm-up load, and the warm-up condensate load is, you got cold pipes, and you're going to make a lot of condensate. So simply put, we're going to have a trap bypass valve. And I know that you have all operated trap bypass valves in the Cenovus lab on the main floor. There's trap bypasses. You warm up a steam line, you open up the trap bypass. Now, there may be some plants where you've got a trap that's hard to get to. It's the end of a steam line or something like that. There may be places where they size a trap for automatic warm-up. But where there are operators present and the operators are on site during the warm-up, we'll have manual trap bypasses. So this would be for a manual warm-up. But we need to make that decision. How much money are we going to spend on the trap? How big does it need to be? Does it need to be sized large enough for automatic warm-up? Or can we just use a smaller, less expensive trap and trap it in with the trap bypass? Now, there's temperature and pressure, again, always a factor with fittings, because we know the relationship between temperature and pressure. And so, we got class 150, 300, 600 flanges and that sort of thing. Well, we also want to make sure that the trap is good for maybe saturated steam at, if our pipe is at 2 megapascals, we want to make sure that the trap has got the similar MOP. We wouldn't want to install a trap that's good for 1 megapascal on a 2 megapascal steam line. Now, another thing is pressure differential across the trap. And all we're going to look at right now is back pressure. So the back pressure on the trap, so back in the old days, before we had mechanical steam traps, some engineers got the bright idea of, hey, look, we can install a fixed orifice in the condensate line. And that way, yeah, maybe sometimes steam is going to pass, or yeah, maybe sometimes condensate might back up a little bit. But it was better than just letting steam blow. Okay, so this would be a very, very early attempt at trying to conserve some of the energy in steam. And then all we did was we added some sort of an operating mechanism that was thermostatic or mechanical or thermodynamic operating mechanism to open and shut or modulate the flow through the orifice. So when we take a look at the flow through this orifice, we've got P1 here, and we got a smaller P2 there, and of course the flow across that orifice is going to depend in part on the delta P as well as the orifice size. So this P2 here is the back pressure, and sometimes we got condensate systems where there actually is back pressure on the trap. And so one of the things we would do is make sure that that is a consideration when we select the trap. We make sure if the orifice is correctly sized, given a particular inlet pressure and given a particular discharge pressure. Exposure to freezing temperatures. Again, you know, sometimes traps are exposed to freezing temperatures, and one of the applications where we see that is with steam tracing. So let's say I've got some bitumen in this pipe or dilbit or something like that. By the way, did you hear that Husky was purchased by Cenovus?
What are your opinions on that, Dave?
I have none, other than I used to work for Husky. So, okay, here's an opinion. I just formed one. Husky is a Chinese company, and Cenovus is Canadian. So, being a Canadian boy, I kind of like us, you know, having more control over our assets.
I think it's a very good move for Cenovus.
What was that?
I said I think it's a very good move for Cenovus, diversifying their assets by acquiring diversified assets.
So one of the things that we find with the oil industry is, you know, the upstream and the downstream. And you see Husky has all of these stations, right? All these service stations. So, you know, when the price of oil goes down, well, they can still maintain the price at the pump, right? So, you know, they can recoup their losses at one end. You know, and of course, all the other stuff that they sell, they have the convenience stores and all that kind of stuff. So yeah, I think it's good for Cenovus in that regard to have the whole distribution network that they've probably purchased. Anyway, getting back to this pipe that has got dilbit in it, and this stuff might congeal or solidify at low temperature. So what we'll do is we'll take a tube, maybe like a 1/2 inch stainless steel tube, and we'll put it underneath the insulation, and we're going to run steam through it, and that's called steam tracing. And then, of course, we're going to have some traps, and those traps may be exposed to freezing temperature. So do we want a trap that's going to get damaged just in case maybe it gets frozen? I mean, we don't want it to get frozen, but what if? Do you want the trap to damage? So that may be a consideration. So if you weren't aware of the term, it's called steam tracing, and it's basically where we use a small steam line to keep something warm, keep something from freezing. I don't know if they do this in Texas. Probably this is like a northern climate phenomenon. So warm-up load. So determining warm-up load. And I think this is actually where we left off. This here is simply MC delta T. Did we actually go through this calculation? I think we did, didn't we? Well, I'm going to look at it again, okay? M is the mass of the pipe. Well, how do we find the mass of the pipe? Where do we look? What do we need to know?
Pipe charts.
Sorry, can
The
you say that
pipe
again?
charts. Pipe charts.
Pipe chart, yes. So the academic supplement. So in the pipe charts, you know, we're used to seeing outside diameters and thicknesses, and then we can calculate inside diameters and stuff like that. But there is underneath where they show the pipe thickness. Okay, so let's say we got NPS 1 pipe, and so there's the thickness, yes, but the lower number is mass per meter in kilograms. Okay, so this 1-inch pipe, SCED 40 is 2.48 kilograms per meter, and SCED 80 is 3.21 kilograms per meter. So we've got the mass per meter, and then we just need to know how long the pipe is. So the mass, now I'm going to put kilograms per meter times the meters in length. And then as for C, well, that's it right there. That is the specific heat for steel. So this formula is all about steel pipe. Now, here's the thing is, does ABSA give you this formula? Or is it in your academic supplement? I think the answer is no and no. But what I'm doing is I'm giving you a way that you can figure this out on your own. C is for steel is 0.494, and that is in your academic supplement. The delta T, T1, is ambient temperature, and T2 is the steam temperature. So how do we find the steam temperature? Steam tables, or it'll be given, one or the other. Now, L is in the denominator, and L is the latent heat of the steam. And so you go, well, what do we use for L? Do we use L is equal to 2257? Because, I mean, that's what it is at ambient, and we're warming up. We're doing this warm-up load and a 101.3 kPa, which we're going to kind of assume is the absolute pressure inside of the pipe as we're warming it up. It's 2257. Well, if we use 2257, it's accurate when we are first starting to heat up the pipe, but we end up with a fairly small value for C when we're actually up to pressure. So let's say, for example, at T2, which is related to the pressure on the steam table, if we find HFG at T2, we might end up with a value for L as being, I don't know, I'm just going to pull this one out of the air, 1980 kilojoules per kilogram. So we now have a smaller number in the denominator, and the net effect is we have a larger value for C. So what's best? The best is we use L at T2, which is really our worst case scenario, right? So what we're doing is we're saying the smaller the latent heat of evaporation that we're using for the steam, we actually calculate a larger condensate load, and it's beneficial for us and our piping system in that regard. Then there is the factoring in the time business. So we can warm up a steam line in 10 minutes and 15 minutes and 20 minutes. And I think that we went over this, this calculation here, and it was Q is, no, pardon me, C is equal to MC delta T over L. And so this one here was the mass would be equal to 30 kilograms. And the particular kind of pipe is DN 200 Sked 40. So DN 200, oh boy, that's big stuff here. That's 8-inch. Schedule 40 has a mass of 42.2. Oh, there's 30 meters. Oh, where's my brain? 42.2 kilograms per meter. And so 30 times 42.2 is 1,266 kilograms. Then we have to deal with T1 is easy. It's given to us. It's given to us as 10 degrees Celsius. T2 will be, well, we're going to do 1350 kPa absolute. So 1350 kPa absolute, what does that give us in terms of T2? Does somebody have the steam tables handy? And if you're doing that, you can also figure out the value for L. So find FG 1350 and the saturation temperature at 1350, please. Somebody, I don't have my handbook handy.
Okay, we'll need an interpolation.
Pardon me?
Okay, we'll need an interpolation. We have for 1, 3, and then 1, 4. 1300 and 1400. So
Okay.
that would be maybe a quick one. Just give me a moment.
T2, anybody?
Okay, T will be 193.355.
Okay. And my silly pen has decided to turn into a cursor instead of a instead of a pointer. So let me just reboot my pen. Now I can't even see my pointer. So you said it's what, 193? Point
355.
I'll just say 0.36. And then what do we get for HFG? That would also require some interpolation too, I guess.
Yeah, just give me a moment.
Are you doing a double interpolation?
Okay, that would be 1966.2.
Again, it's not working. 1966.2?
Yeah.
Okay, my pen has stopped working, so I can't write or do anything. So I'm just going to flip the page. Okay, and so then here is your answer. And if I recall, we were, this is kind of where we left off, right? So we reviewed a little bit, but I did take sort of a little bit of a different approach. Now, as for this business here, I really don't like the way that they've done it. They've said, we're going to do this over a period of 10 minutes. So think about this way. We've got 58.33 kilograms is what we are producing, warming it up from T1 to T2. And we're going to do this over some period of time. In this case, it'll be in minutes. But there's nothing to say we can't use seconds or hours, you know, whatever we want. But in this case, we're using minutes. So we know that there is 60 minutes per hour, and we are going to do this in 10 minutes. And so the minutes cancel, and they leave us an answer in kilograms per hour. So that's from the Penn Global. If you want to work on one, you know, we can do another one if you like. In this case, we've got 52 meters of DN50 Sched 80 being warmed from 18 degrees to its final steam pressure of 2 megapascals absolute. How much condensate forms during warm-up, and if the pipe is warmed over 25 minutes, what's the trap capacity required? You want to do that? Or you can practice it on your own if you like. You know how to get the numbers. You know how to do the calculations. So what we end up for this particular one is 19.6 kilograms, and 47 kilograms per hour would be the minimum. So this is the new stuff. And so in your Penn Global, they have this table about condensate load. Now, this is how much condensate forms during normal operations due to radiant heat loss. And so you see on the far end, you know, there's 1724. Basically what we do is we look up the working pressure of the steam pipe. And then we also look up, you know, the size of the pipe. And then what we have is it tells us what is the square meter per lineal meter. So there's length. Square meters is a surface area per length. And then it'll spit out numbers. At 103.4 kPa, this one will produce 0.18 kilograms of condensate per hour per meter. And this 3-inch pipe at 413.7 produces 0.27 kilograms per hour per meter, and you get the idea, right? So there are tables and charts available, and usually they would be from the trap manufacturers like Armstrong or Spirax or something like that, Yarway. And so what you can do is determine what is the radiant condensate load for normal operations. This is not a warm-up load. It does not include the amount of condensate that's formed while you're warming up a pipe.
Why is it in such weird pressure?
Why weird pressures? Because what PanGlobal probably did here was they took pressures in PSI and did a direct conversion instead of doing a soft conversion. Okay, I mean, if it was up to me, I would call this one 100, and I would call this one 200, and I'd call this one 410 or whatever, right? And this one here would be 1725. That's why they're weird pressures, because somebody with a calculator converted the numbers directly from US standard units. Kind of silly, hey? But then PanGlobal goes on to say, hey, look, if you don't have the formula, or pardon me, if you don't have a chart, you can use this formula. And so we see then that the condensate load is in part proportional to the lateral surface area of the pipe, or the external surface area of the pipe. Then there's also T1 and T2, and we know that that's the delta T. For some reason, what PanGlobal has done is sort of switch them. I always go, I take the final condition minus the initial condition, and that gives me a delta. But what they've done is they've turned it around, T1 minus T2. Okay. It's the same thing, you still get a delta. And so, yeah, we totally get this area business, right? Surface area. And the answer that we're going to get is going to be in kilograms per hour of condensate. But let's take a look, and we know what L is, right? L will be HFG at operating pressure. But let's take a look at U. What the heck is U? It's the heat loss from uninsulated pipe in kilojoules per square meter per degree Celsius temperature difference per hour. Where the heck are you going to get that? I don't have a clue where you're going to find that. No idea. And E is efficiency of the insulation. 1 minus efficiency. Where are you going to find? I don't know. I don't have a clue. The question is going to have to give you that information. But here's the bottom line. This formula is not in your PanGlobal academic supplement. And as far as I am concerned, is ABSA will not give that to you. They're not going to test you thing that doesn't have a formula that you can refer to in the academic supplement. I can't see that happening. And I also believe that ABSA is not going to give you a chart to work off of. They're not going to do it. So are they going to give you U, and are they going to give you E in the question? No, because they're probably not going to give you the question, period. So here's the thing is, I am not going to test you on this. You won't get this on a quiz or a final or anything from me. My opinion is this is in there for your information so that you know that you can look up tables from the various manufacturers and you can determine the radiant heat loss from the pipe and how much condensate is going to be formed based upon the diameter of the pipe and the length of the pipe and the operating pressure. All right. Enough of that. So we've determined how you figure out the load. And what we're going to do is we have to match a trap to the load. So the trap capacity has to reflect what it is we want the trap to handle. So we know about the pressure difference across the trap because we mentioned back pressure, and I'm not going to go over that again. But back pressure obviously affects the capacity, but it's important that we know the capacity increases. The capacity of a trap increases as the steam line warms up. And as the steam line warms up, it comes up to pressure. As the operating pressure increases, then of course the delta P across the orifice of the trap increases, and it will be able to relieve more, a greater amount of condensate. Now, as for the discharge orifice, when we purchase a new trap or replacement trap, usually there's that information in there, and you may have a selection of several different sizes of orifice depending upon how much condensate you need to discharge per unit time. And now we get to the subcooling business, which is a little bit different. And so let's consider, first of all, condensate that hasn't subcooled very much. In other words, it is closer to its saturation temperature. Because there's a delta P across the orifice, it's going to flash. And when it flashes, it's going to actually stay in the discharge orifice. It's actually the flashed steam is going to occupy some of the flow area of the orifice. And in doing so, that is going to be an obstruction. So if we're closer to the saturation temperature, then we get more flashing and less capacity. But if we are subcooled more, we get less flashing and more capacity. So how do we install them? First of all, what we need to know is that every fitting that we install, and these are fittings in a piping system, according to the B51 code, CSA B51 says that they have to have CRNs. And of course, they have to have the right capacity, and they have to have the proper pressure rating and temperature rating. They should be accessible for maintenance. Now, as for this thing, installing them backwards, usually traps have arrows on them that show inlet and outlet. Okay. Now, sometimes traps do get installed backwards, and so if we got a trap that's not working, maybe that's an issue on a newly installed trap. So good to kind of check something like that. But be careful if you're installing a new one. Pay attention to the directional arrows or where the inlet and the outlet is. Other things we got going on. We have a gate valve here at the inlet to this trap, and we got another gate valve at the discharge of the trap. And so then those are both there for isolation purposes. So we can take the trap out and replace it or service it. We're going to have a couple of unions, one at the inlet and one at the outlet. So we do a lockout, tag out the inlet gate and the discharge gate, let the thing cool off. We can drain it using the test valve and the sediment strainer, and then we open up the inlet and the outlet. And by the way, this is another good example of how a trap bypass can come in really handy, because while the trap is out of service, I can crack open the trap bypass and deal with the condensate in that way, so no condensate backs up. Now, other things we've got going on here is we've got a strainer, and sometimes the strainer is actually built into the trap, which is kind of a nice feature. And the strainer should, but they don't always have, but they should have a blow-off valve so that you can discharge the dirt and the crap that builds up inside the strainer on an ongoing basis. You know, so when you're doing your rounds, you can open up that blow-off valve and give it a little shot of steam and blow the crap out of the strainer. If the strainer gets obstructed, then it's going to back up condensate. So we want to make sure that strainer stays clean. And then the last thing in this picture here is this test valve. And the nice thing about the test valve is it's a beautiful way of testing the operation of the trap. If the trap is in service, I can shut my discharge gate valve and I can open up this test valve. And if I know the discharge characteristics of the trap, then I'll be able to determine if the trap is functioning properly. So when I open up the test valve, I will see some flash steam come out, yes, but it'll be a fairly small amount of steam. But mostly what I'm going to see is condensate discharge. So the flash steam will be a smaller component, but if I see billows of steam just pouring out, like steam just blasting out like I got an open steam line, then I know that the trap is passing steam. It's not closing correctly. So a test valve is a very important way of us determining if the trap is functioning properly. It's very simple. If I'm on my rounds, I close the gate valve on the discharge, open up the test, and see what kind of discharge is coming out. Does the trap discharge continuously? Does it discharge intermittently? Well, that's one of the characteristics of the trap itself. So if I know what kind of trap it is, what its discharge characteristic is, then when I open up the test valve, that's what I should see going on. Now, unfortunately, in the real world, this test valve, when the bean counters are looking at the cost of installation of the whole plant, they're going to say, do you really need a test valve? Let's get rid of that thing. And so you're going to find a lot of plants, the steam traps do not have test valves. They're really beautiful when they're around, but if they're not there, don't be surprised. So the next thing is the piping should be full size to the inlet and the discharge of the trap. The piping should always be sloped toward the trap so that the condensate goes into the trap. And then this one here says trap each equipment separately. So let's have us a little look at that. Why would we want to trap each piece of equipment separately? Well, here's a couple of heat exchangers. Heat exchanger number 1 and heat exchanger number 2. And each one is fed by steam. And so what I have here is a control valve and another control valve. And each of these exchangers might have a different load. So maybe this one here has got a lot of steam going in it because the load on this exchanger, it's got a high load, and so it's using a lot of steam. And maybe this same one here at the same time has a low load. It's a heat exchanger that serves a different system. But because this one here is under a low load, it's not getting much steam at all. So can we save money by hooking up them together and using a single steam trap? Well, what's going to happen is the pressure in this vessel, the steam pressure, is going to be greater than the steam pressure in the other one. And what we're going to do is just blow the condensate and steam up into there. Okay. So to make a long story short, we trap each piece of equipment separately. This situation here is no good. Each vessel is going to have its own steam trap. So we'll end off the first 50 minutes with this particular slide here. So the B31.1 Power Piping Code doesn't just cover steam lines and feed water lines and blow off and stuff like that, but also steam trap piping. So what does the 31.1 say about steam trap piping? Now they use the term drip line, and we often use the word drip leg. And a drip leg and a drip line, it's the same thing. Just, you know, you need to know that they mean the same thing. So the first one here says under paragraph 122.11.1, it says that when you got drip lines from equipment that operate at different pressures, shall not be connected to discharge through the same trap. And I think that my previous example demonstrated that pretty well. And 122.11.2 is about discharge piping itself, because here's a trap and we've got a drip leg going into the trap, and we got the condensate leaving, and we got the inlet has got a particular mop, which is going to be the allowable working pressure of the steam piping. But what about this here? What do we do for the mop at the discharge? Well, if we have a condensate system that is vented to the atmosphere, then what we have is a zero gauge pressure in the condensate line. And so if it's vented to the atmosphere, it does not require the mop of the inlet piping. But if there's any way that we can pressurize it, so like let's say we put a valve there. If we put a valve there, then the pressure downstream could potentially equal the pressure upstream. So once we have a valve at the outlet of the trap, then the mop of the discharge piping has to be equal to the mop of the inlet piping. Anyway, that's covered under this discharge piping bit, and you can read that over. This is actually all in your Pan Global as well. That's in the chapter. So good to know that, again, you can look at the 31.1 code for some of this information, and you should also know that that code is permitted in your ABSA exams. So if you do have the 31.1, good on you, and you can open it up and find chapters about discharge piping for steam traps and what have you. So let's take a break. We'll see you back at 11 o'clock. Hey, is you calling about that student? I just looked at the email right now. I thought, oh, Clayton's in a panic. He's calling me. Just so you know, I only got a couple of minutes here because I'm just taking a break between classes. So, what do I think? Wow. Saturday. have? No, it's UTSAV, UTSAV, Patel. Yeah, but I know that I had him in the first rotation. So I'll take the configuration. Well, if you wait a little bit, if you can wait an hour, and once I'm out of class, we can kind of work on this together, try to figure out whether you or I. All I know is, as long as it's close to okay, so maybe they stay in the same group, what do they do during lunch break, break time? You know, they know that the guys on the other side, they get together. But that's what you're calling it, though, eh? Yeah, well, this guy here, his name is UTSAV, UTSAV. I remember that very well. I had him in his rotation. Oh, he put UTAV later, UTAV, but earlier on it said his name UTSAV, so. Well, Patel us, yeah, right? Yeah, well, ask him for the student number, just to make sure, just to verify who it is. But I think that what it is that he, you know, has spelling deficiencies, right? You read any of his, you know, things. So, yeah, that's fine. It's fine. And I'm in a class with him tomorrow, so. Okay. We're back, and I got a pointer that's working again. Let's see how long it lasts this time, eh? Let's do it with purple. Maybe purple's my lucky color for today. So the next objective, number 4, is about procedures for commissioning, testing, and maintenance of steam traps. Okay. So testing of steam traps. Now this is not in your PG. This one right here, this automated continuous monitoring. But you know, let's welcome to the 2020s, right? So this is what's going on right now, and this is really, really cool. Continuous steam trap monitoring. So you know, one of the problems with steam traps is either A, they blow steam. If they pass steam, there's a huge energy waste because we're not capturing that latent heat, right? We spent all the money on fuel to make latent heat of evaporation. Now we want to recover that latent heat of evaporation in some kind of a heat exchanger. And if we are blasting steam into the condensate lines, we've got a real problem. Number one, we can get water hammering the condensate lines, and number two, we're not using the energy that we paid for. So there's a huge cost and a huge efficiency loss in having steam traps that pass steam. And then the other part of it is, well, what if it's not passing at all? What if it's actually waterlogged? What if it's backing up condensate, and that condensate might get into the steam line? Or at least the condensate is occupying part of the heat transfer surface in a heat exchanger, and then we've got an inefficient heat exchanger. We're not getting out of the heat exchanger what we're supposed to be getting out of it. So nowadays, here's what we do: is we put a little device on there, and it is self-powered. It doesn't have a power supply. It doesn't have batteries. You don't plug it in. Nothing. What this thing does is it works on what's called the Thomson effect, the Seebeck effect, and the Pelletier effect. So in other words, what we have is a cold junction, and we've got a hot junction, and like a thermocouple. That's how a thermocouple works, and it generates its own electricity based upon the difference between the ambient air and the temperature of the steam in the pipe. So that is number one, really, really cool. We don't got to replace batteries. We don't need a power supply, nothing. It's self-powered. And then what we're going to do is we're going to have a little temperature sensor here, a little thermistor, and another little thermistor, say, over here. And they're going to be connected to a little brain that's in there. And the little brain is going to have some sort of a Wi-Fi signal transmission, so we don't even have to run wires through cable trays and stuff like that. It'll have some sort of like a MAC address and whatever, and some sort of a program in the vicinity that monitors maybe, I don't know, 100 steam traps. Okay, and so if you're sitting in the control room and you wirelessly address all of these different steam trap monitorings stations, and it'll tell you, is my steam trap waterlogged? Is it passing steam? Is it working correctly? And now you can pinpoint exactly where to direct your maintenance dollars. And I tell you, it's real time. It is effective, and it saves energy. This is the real world. This is what's coming online over the last 10 years or so. Okay, this is state of the art in 2020. Look at that, I can't even print in 2020. That's what 2020 is like. So here, welcome to the present. But do you work in a place that's got all these fancy gizmos? Maybe not. Maybe you just got regular steam traps. Well, one of the best things that we can do is if we've got a test valve, we can use that. Perfect. But there are other things that we can do. We can monitor, just like this continuous automated monitoring system does. We can measure the temperature here at the inlet and the temperature at the outlet. And so let's say I've got a steam temperature of 190 degrees Celsius. So that's the saturation temperature. If I measure the temperature here at T1 and I say that it's 190 degrees Celsius, and then I measure the temperature at T2 and again it says 190 degrees Celsius, well, I got a problem. If it's a thermostatic type of trap, I definitely need to see subcooling. Maybe 10 degrees subcooling, maybe 15 degrees of subcooling, something like that. And even if it's a floating thermostatic or other mechanical trap, it'll be subcooling. So I should see a lower temperature. So if we've got 190 and 190, that's a problem because that means that we're blowing steam. Now, what if I measure the temperature at the inlet and my temperature here is 90 degrees Celsius? And I measure the temperature here and it's, I don't know, 85 degrees Celsius. But wait a minute, my steam is 190, my saturation temperature is 190, and I got 90 at the inlet, and I got 85 at the outlet. What's going on there? What we have there is a trap that has failed closed. Okay, and so now it's waterlogged and it's backing up condensate, and the condensate's residing in there for so long that it has a lot of time to dissipate heat and cool off. And then, the best case scenario would be, let's say at the inlet of the trap, we've got, say, 185 degrees Celsius. And at the discharge of the trap, maybe we've got 170 degrees Celsius. And that's good. I've got a delta T that indicates subcooling, and actually it'll probably be less than 170 degrees. Let's say maybe it's 105 degrees Celsius. If I have very little back pressure, maybe it'll be 105 degrees Celsius. Okay. The main thing is I've got subcooling. I've got a delta T across the trap, and so now how do I actually detect that? There are a couple of different ways. I could use a contact thermocouple and measure the temperature there and then measure the temperature there. Or what I could do is take, one of those infrared temperature guns, shoot the temperature there and shoot the temperature there. Or maybe what I could do is use crayons. So we have these crayons that have a known melting temperature, and so I can apply the crayon there and it melts over there, and I apply the crayon over there and it doesn't melt, and then I know that I've got a delta T, a delta temperature. So I heard a little bloop. Does that mean that somebody's trying to ask a question?
Yeah. I was going to ask, in this diagram, where does the condensate go out? Just kind of
In this
wondering.
image that you see here,
Okay.
the condensate's going in. So this is our steam line, and this is actually from our drip leg. So steam and condensate go this way, and then the condensate discharges that way.
Okay, so how does the steam get back to the system?
How does the steam return?
Yeah,
Okay,
like
so let's
temperature.
say I've got a heat exchanger here, and there's my steam trap. And so traps could actually just discharge onto the ground. You know, they could discharge outside and go onto the field or something like that. I've seen situations where it's been like that, but mostly we want to recover the condensate. So what we'll do is we'll put the condensate into a tank. And you've seen these in the main floor lab. You'll see small condensate tanks that are right beside the boilers by the mud drums, right? Because we put steam onto the mud drums to keep the boiler warm during its non-operational period. But anyway, so the condensate will accumulate in a tank, and the tank will have a float, and that float will operate a pump. And the pump then will start and stop according to the level inside the condensate tank. And then it could go in a few different places. So depends upon the plant, but you might have, say, a very large condensate receiver. And that would be in the powerhouse. And so maybe we've got a whole bunch of condensate tanks with their own little pump, and they all pump back into this main condensate tank. This one here is big, right? This one here might be, I don't know, 10,000 gallons or something like that. And then there usually would be some sort of a level control, and we may actually put our makeup water into this condensate tank. Then from the condensate tank, the main condensate tank will have a condensate transfer pump, usually a few of them. And the job of the transfer pump, you can take the condensate and it's going to put it into the heater compartment of our deaerator. And from the deaerator, of course, we've got our boiler feed pumps. Does that answer your question?
Not really. It's there's something that has been kind of confusing for me. Okay.
Okay.
The steam trap is meant to, like, trap in steam and then let out condensate. But I'm just thinking,
Yes.
does it mean that, okay, when the steam is kind of trapped in, it's kind of still along that inlet line? I was just wondering, is there a way it like goes back, from a different line back to the system or something? You
Well,
get my
okay.
question? Yeah, it's like
And
it's trapped in, like it's on the inlet line of the condensate and the steam mix, or is it like there's a way it like goes back to the system? It's kind of
well,
confusing.
the only way that the condensate goes back to the system is it has to go through the condensate system
No, I mean
to the
steam,
boiler
the
to pump
steam.
it back into the boiler.
I mean the steam, not the
But
condensate, steam. We're meant to
the
like
steam,
keep the steam in the system and then let out condensate. Okay.
sure.
So I'm just thinking, so how do we kind of keep back the steam in the system, considering that, okay, from the diagram, the inlet, it has a condensate and steam mix initially. So it's like, okay, keeping the steam means, okay, you have it like along the line or something. I'm kind of confused with that part.
Okay. Let's see if this can answer your question a little bit better. This diagram that I've shown of some kind of a heat exchanger has a pool of condensate in the bottom. Normally we wouldn't see that. I just use that for illustration purposes. Think of this thing as being all full of steam. Now, as the condensate forms, it will run down through the pipe and into the body of the steam trap. Now, some steam will actually go through that pipe as well. So we get both steam and we get condensate, and it really depends upon where the trap is in terms of its operating sequence. Is it discharging or is it closed? And so when it's discharging, we can actually get steam flowing from the vessel into the trap while it's discharging. And as soon as it detects the steam, then it stops. So what we end up with is steam in the vessel, yes. Steam in the inlet piping to the trap, yes. Steam inside the body of the trap, okay, until it radiates enough heat that it condenses. And of course, as it condenses, it will flow into the trap and cause the trap to operate again. Does that better answer your question?
Yeah, yeah.
Okay, I'm glad because okay, so it mentioned temperature, so I can measure the temperature at the inlet, I can measure the temperature at the outlet, I can use a crayon, and these are very special crayons, and you can buy them. You go online and you look for steam trap testing crayons, and and sometimes I see engineers walk around with them in their pocket, and they just, you know, test the traps that way. Then there also is an ultrasonic listening device. And so you put on these headphones and you got this probe and you're listening to sounds. And I got to tell you, at Red River College, when I worked there as an assistant shift engineer, they had this thing and they'd put it on my head and say, hey, Dave, go and check the traps. And I had no idea how to use it, and I had no idea what I was listening for. And honest to goodness, and then I come back to the powerhouse after 2 hours and they say, well, what did you find? I'd say, well, what am I listening for? And then the shift engineer would shrug and go, well, I don't know. Listen for a trap that's not. Like, what does that sound like? I don't know. So I really don't know how effective these ultrasonic listening devices. I think you'd have to take some kind of a course in learning how to interpret the beeps and sounds that this thing makes as you're actually listening to the trap. But the whole idea is, if you know that a bucket comes up and then it goes down, or a disc opens and shuts, or if an F&T trap makes a hissing sound, then hopefully you'll be able to differentiate between all of these different sounds and say, oh yeah, the trap works, or no, it doesn't. Frankly, I don't think it's very effective. I think temperatures are far more effective. Which brings us to maintenance. Okay, on your regular rounds, you should blow out the trap strainers. Okay, so you're walking around on your rounds, open that valve for 5 seconds and close it. And all you're doing is, there's a strainer in there, and that strainer could be obstructed with dirt and debris and sediment, and you're just blowing it out to make sure that the steam and condensate can effectively get to the trap. And then dismantling annually and repairing and blah, blah, blah. So this is a big thing in many powerhouses. The power engineers, when they're on their maintenance rotation, in the summertime, maybe it's a heating plant. During that period of time, you take apart all of the traps and rebuild them. That's a pretty common thing in many large heating plants, like say SAIT. But here's something that we don't often think about. Each trap should have its own ID, and then we can keep records for that trap as for when it was last rebuilt or replaced. Or what is the type of trap? The manufacturer, the size, the type of trap. You know, you can keep all this information, and so record keeping of traps is something that probably is not done as well as it should be done. So for steam trap commissioning, text has got this big procedure. So let's say this is a new trap here. So here's the big procedure. You can kind of reason this out yourself. Before I install the trap, I'm going to have the inlet valve shut, and I'm going to have the discharge valve shut. And what I'm going to do is I'm going to put a cap, a pipe cap on the end right there. So I haven't completed the installation. And then what I'm going to do is open up this valve and open up the inlet. And what I'm going to do is blast the steam and crud and debris out, because maybe there's scale and rust and dirt inside of this pipe. And we want to make sure that's all clean before it gets to our nice brand new trap. So after we blow it for a reasonable amount of time, then we're going to close this valve and let it cool off. And then I'm going to remove the bonnet, and I'm going to pull out the strainer, and I'm going to get all of the garbage out of it and make sure it's nice and clean. Then I'm going to put the strainer back in and close this up, and I'll close that valve. I'll remove the cap, I'll install the trap, and then what I do is I open up the inlet valve and I let any steam and condensate in there sort of build up in the trap. And then once I know that there is condensate in the trap, I can open up the test valve and see if it's working properly. And then I can close the test valve and I can put it back online by opening up the discharge. You can kind of reason your way through that kind of sequence. The main thing is, what we want to do is clean out the pipe, trap any debris and sediment, and if we have trapped debris and sediment, we're going to clean the strainer to protect the new trap. We'll make sure we follow LOTO, because we don't want anyone getting hurt during this. And if we can, we'll test the valve or test the steam trap before putting it online. The next topic is condensate induced and flow induced water hammer. We are not going to talk about flow induced water hammer because that's like pumps starting and stopping and check valves slamming shut and stuff like that. So that would be fourth class stuff. I'm going to say very, very little about steam and condensate induced water hammer. This is going to take us less than 5 minutes. So we know what water hammer is. We know how destructive it is. We know that it damages pipes, damages equipment, and kills people. So it happens when we got saturated steam and condensate together in the pipe. So that saturated steam is at saturation temperature, and the condensate can cool it off and cause the steam to collapse. And where we get collapsing steam bubbles, we end up getting condensate drawn in. And of course, this collapsing steam bubble changes in volume like 1,600 times. And we get these enormous shock waves. So why do we get it? Maybe we've warmed the steam line up too fast. So when you're warming up a steam line and you start to hear water hammer, best to slow down. Shut the valve. The energy is coming from the steam that you're putting in. And if you close the valve, you shut off the energy supply, and you should see the water hammer stop. Then you can start warming up the line again by admitting steam, but slowly. Okay, don't warm up the steam line aggressively, because you might exceed the ability of a trap to discharge the condensate. Okay, maybe the trap is sized for a warm-up load, but you're warming it up so aggressively that you are exceeding the rated warm-up load or the design warm-up load of the trap. Then you're going to get condensate backing up, and you're going to get steam-induced water hammer. Poorly graded steam lines, of course, they must be sloped correctly toward the traps. poorly supported and sagging steam lines, again, we've got hangers, or maybe we've got roller guides. Well, if the steam pipe has come off of the rollers, then what we're going to get is a sag. Or if we've got a pipe hanger that has come loose and it's just dangling, the hanger rod is hanging below the pipe. In either one of those situations, we get sagging, and the sagging makes an area for condensate to build up. And if we don't happen to have a trap there, then what we have is a location where water hammer can occur. So one of the things we're going to do when we do our regular rounds of the plant is we will look for broken pipe hangers or missing pipe hangers. Easy to see. We don't need to take a fine-tooth comb. We don't have to inspect the piping very closely. You can tell when you see that pipe hangers are loose and the pipe is wobbling around, or if you see that one is broken, you can see parts of it dangling underneath the pipe, or you can see when the pipe isn't on the roller guides. Now, undersized traps is a no-brainer. Failure to open bypasses on startup, that's a no-brainer. Malfunctioning traps, if they fail closed, that's a no-brainer. Now, here are a couple of things that I do not believe are in your Pan Global. Maybe the bottom one here is wet pipe insulation. When pipe insulation is wet, it's no longer an insulator. Wet insulation, in fact, is a conductor of heat. Which is contrary to what we want it to do, right? And the more heat is conducted out through the pipe, the greater the rate of condensate formation. So if there's wet pipe insulation, we're going to make a note of it, and we're going to get the maintenance crew involved in replacing the wet pipe insulation, maybe replacing the cladding. Maybe the cladding is off and the rain came and made the insulation wet. But here's one that's very, very important. Now this happens, let's say that there's a steam line that's undergoing some modification. Maybe they had to remove 5 meters of insulation so they could tie in with an elbow and run a new branch line or something like that off the steam line. And they never get around to putting the insulation back. Well, the insulation is there to reduce the amount of heat loss to the environment. If it's missing, we got a high amount of heat loss to the environment and a higher rate of condensate formation that may exceed the ability of the trap to remove the condensate. So this one here, if I can find an online case study, there's one in particular that I was reading about where they had something like 50 meters of pipe, and the company was pushing to get this pipe back into service, and so they actually put steam in the line before insulating it, and over the period of a weekend, hammer badly that it blew up the steam line, and it was in a steam tunnel, like an underground tunnel, and it killed an operator. Why? Because pipe insulation was missing. So if you see missing insulation, report it and get maintenance on that ASAP to replace the pipe insulation. And here's a couple of things that aren't in the Pan Global, but they are in the Pan Global. They're just kind of in a different chapter. Again, we need to watch the boiler water level, and we also want to watch the boiler dissolved solids, because we can have foaming, we can have priming, we can get all kinds of conditions that give us carryover. And carryover isn't really something that's taken into account when we're sizing steam traps. We don't size steam traps for carryover because we assume there will be no carryover. So this is about boiler operations and operating your boiler correctly. I believe that in your 4th class there's a case study about a steam line blowing up, and I can give you first-hand knowledge of that particular incident because I know the plant, and that was actually, those were excerpts of a letter that were sent to me by the operator of that plant. So yeah, pipes blow up, people die when insulation is missing or when boilers are operated incorrectly. So we may in fact get water hammer in condensate lines. So let's take a look at some of these considerations to prevent it in steam lines and condensate lines. Proper sloping, or as what it said in the other slide, grading. Grading and sloping, that means the same thing. So we always make sure that the steam lines are sloped toward drip trap. And we saw in the early slide, where do we put them? That covered this stuff. But here's something a little bit different. Every 90 to 150 meters along the steam piping. So we've got a really long steam line. We'll have a drip leg and a steam trap. So even though we're not at the base of a riser or anything like that, still we should trap it every 90 to 150 meters. The rest of the stuff we've looked at in that early slide. But here's an interesting arrangement where we've got a steam line and we've got a condensate return line that's situated above the steam line. And so the discharge from the steam trap goes through here and goes up a particular height, and then it goes into the condensate return. And you might think, well, why on earth are they doing that? Because there's back pressure on the bucket trap, and we don't like back pressure on the trap, and blah blah blah. Well, sometimes the circumstance, it's just the way it is. It's the way the plant is designed. You've got pre-existing equipment. Sometimes this is going to be the situation. What happens is when this trap discharges, you're going to get condensate in this line, and it doesn't actually drain. So we end up with this vertical leg of condensate. Now you got, say, 2 megapascals in the steam line, or 4 megapascals, whatever the pressure is, and the condensate return line is going to be 105 kPa absolute. Okay, so we've got a delta P, and so when the bucket trap opens, we're going to get flash time that trap discharges. And that flash steam is going to condense in this vertical line, and we're going to get water hammer. I don't know what we can do about this. I really don't. Maybe particular types of traps that have got more continuous discharge than intermittent discharge might be better in this type of application. But regardless, this is not a preferred situation. Are there plants like this in certain locations? Yes. But so now maybe there's a trap that deals with this situation better. Wow, look at that. Objective 6 is done. So this one here is all about a steam system startup, and you have done this so many times in the Cenovus building that I'm not going to go over it. You can read on your own. But involving the rate of warm up, making sure the trap bypasses are open, blah, blah, blah. So the next thing has to do with insulation. pipe insulation, in particular thermal conductivity, and basically how much heat is transferred per unit time through conduction. So I'm going to give you a formula here, and you tell me if you recognize this. Or you might see it like this one here. Instead of K, they'll use lambda alpha T delta T. Shout out if you recognize the formula.
Isn't for thermal conductivity?
Yes. Are you doing this in thermal right now?
We did it already.
You did this already?
Yes.
Perfect. Who's your thermal teacher?
Bruce.
Okay. All right. It's funny because the other class hasn't done this. Okay, so K might be they might use the letter lambda. What's that?
When did we do this, Manny?
Was in the first first module or second module.
So D, we might use the small letter S, or we might use the letter L. And so D is the thickness of the insulating material. So I'm not going to spend a lot of time on here. K or lambda refers to the thermal conductivity of a material. This is a physical property of whatever the material happens to be. So for example, is it fiberglass insulation? Is it asbestos? Is it calcium silicate? Whatever. So every particular insulating material from a particular manufacturer, and part of this is based upon the manufacturing method, is going to have its own unique thermal conductivity. So it's a characteristic of a particular material. And the unit for the thermal conductivity is watt per meter Kelvin. Okay, watts per meter Kelvin or watts per meter degree Celsius, whatever. And D or S or L is the length of the heat transfer path. So in other words, this is actually the thickness of the material. So what I want to look at is K and D. And what I can do is rewrite this as Q is equal to K over D, or lambda over S, or whatever you want to do, times the area, the heat transfer area, times the time that we permit the heat transfer to take place, times the delta T, which is the temperature on one side of the material minus the temperature on the other side of the material. But now what we've done is we've kind of isolated this term K over D, and so what we have then is the thermal conductivity per thickness of material. Per thickness. And so let's think about this. If we've got a material that's super thermally conductive per a given amount of thickness, then we got a lot of heat transfer. So if we've got a big K, so if K is a very large value, if K is big, then the amount of heat transferred is also big. So what makes a good insulator? A good insulator good insulator has a very small K. Well, next slide covers that. Okay, so here's our K over D thing again, and K is something that is very common in Europe. In Europe, they're more about first principles, and thermal conductivity makes perfect sense to the European mind. Whereas the North American mind likes to use this kind of shortcut. So the next time you are in Home Depot or Rona or whatever, you're going to see insulation with a particular R value, and you'll see things like R, R12, you'll see R20, you'll see R40 insulation. And what is R? R, in fact, is equal to D, the thickness of the material, divide that by its thermal conductivity. Okay, it's the reciprocal. And because R is D over K, then we can replace K over D with R, but R then has to go into the denominator. So we say a good insulator should give you a very small Q. So in this case, if we've got a very big R, if R is a very big value, then Q is small. Or I could write it this way. Big R is equal to a small q. Or if the R value is small, then we've got a big Q. So they're inversely proportional. Now, I don't know if you did any work in thermal with R values as well, but I think that you need to know this, that the low K factor is a good insulator, or high R value. Why? Because of their position with regard to whether they are in the numerator or whether they're in the denominator. Now, I don't have any questions for you to work on, but you can look over what's in the textbook and work over that on your own. Now, as for insulation maintenance, we know that we don't want it to get wet because then it becomes conductive. We also don't want it cracked or broken. But insulation should always be protected by cladding. And the cladding could be metal cladding, and you've seen that. And you've also seen this, fabric like canvas. The steam lines, you'll see, you don't see the exposed insulation in the lab. You see the insulation that has a canvas cladding that's been painted. So this is very for protecting it from moisture or damage. We never walk on insulation or stand. We don't lean ladders against it. We don't put heavy stuff on insulation because it's going to compress it. It's going to damage it. It's going to reduce its insulating value. If insulation is missing or hasn't been removed, replace it. And if it's not replaced immediately, people might get burned or water hammer. So let your maintenance people know. Now there is some other stuff that I didn't do. And so for example, there's Objective 9. Objective 9 is identify the most common industrial insulating materials. You know what? Boring. Read it on your own. And then under Objective 10, there's methods of applying insulation to piping and equipment, wrap and clad, blah, 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 blah. So again, read it on your own. And that's all I have for you for today. We have actually some time for some questions. Hallelujah. Are there any other questions? Anything else that perhaps you wanted to look over? Anything I can help you with your understanding? Then it's goodbye. And we'll see you tomorrow at 11 o'clock. And tomorrow we're going to be doing valves and actuators. So read ahead. Read A to chapter 6.